of Calculus 3, and in this part we all get into chapter 6. It's vector fields. 6.1. I think the section is 6.1. So first let's take a look. What is a vector field? A vector field, it is a vector valued function of vector variables. So in the two-dimensional case, a vector field, it's a function of a vector, x and y. Consider x and y as a vector. Okay, so it has two components, and along the x direction and the y direction. P is a function of x and y. Q is also a function of x and y. This is a two-dimensional vector field. And also we have three-dimensional vector field. The function is three variables, and there are three components as for the function value. And we can write the vector value function using the component form or using the linear combination of I and j. And also, you may wonder, why do we have to consider vector field? Because they are all actual things which can be considered as a vector field. Okay, in physics, the force field, and indeed it just this chart roughly shows the gravity field of the Earth. Actually, it has an interaction with the gravity from the moon. But anyway, let's say this is the force field of the gravity of the Earth. Okay, only consider those red lines. And also that is the gravity field or vector field. And also you can consider this is kind of it's the flow of the river. There's rock somewhere in the middle of the river there. So basically this tracks how the water moves along, and from left to right, and the circles around rock, this kind of situation. This indeed it is a velocity field, which is also a vector field. Okay. And then the real question is, how do we generate those vector fields? Okay, both are two-dimensional cases, and certainly we could have three-dimensional vector fields too, and it will be more complicated. For our consideration, we are just going to use two-dimensional vector fields. So a very simple example: f of x and y along the I direction. Well, it is claimed that the function of two variables, but anyway, only one variable will count, x over 2. Along the j direction, that's y over 2. So what you can do here is you are going to, like we plot the graph of one single function, one single variable. You take some random values of x and find out the y value, plot the ordered pair. This time it is more complicated, okay, because each time we are having ordered pair as a set of values for the function. So I'm choosing random, somewhat not necessarily random, but anyway, you really can choose any random values. And again, for class purpose, usually we just make some simple and easy choices, x and y in this fashion. And then keep in mind at each point there is a vector. And indeed at the point 1 and 0, we are having a vector 1/2 and 0. And then if you track, I guess it's a little harder to trace from this graph, and you really want to plot very carefully. Each point is a different vector. And then eventually, if you plot all those factors carefully, you will see somewhat a surprise situation. What I'm seeing here is somewhat we are having something pulling away from the center. And furthermore, when we move farther away from the center, the force, it is getting big, right? Everything is going away from the center. Everything is going away from the center in all directions. The farther you go, the faster it goes away, right? Or it's a stronger the force. If it's a force field, if it's the velocity field, then consider that's the faster it goes away from the center. So that is roughly the idea of a vector field. Force field, it is a vector field. Velocity field, it is a vector field too. And also I want you to know, indeed, if you think very carefully, vector field, it is not totally new to us at all. And indeed, we did mention the gradient of scalar valued function, right? The gradient from a function of two variables, that's two-dimensional vector, and the gradient from a function of three variables, that's a three-dimensional vector. Each case, the gradient is a vector field. The gradient, it is a vector field. So that is what I'm saying, the gradient field, it is not necessarily a totally new topic. And specifically, we have little more material about the gradient and the vector field. Okay. And in the case, if a vector field turns out to be the gradient of scalar value function, or really, I'm sorry, in writing, I just wrote it as the gradient. It is scalar valued function. And then we say the vector field, it is a conservative vector field. It is a conservative vector field. And then accordingly, the scalar valued function, f, the lowercase f, it is a potential of the vector valued function f. Okay, and we will have a little more discussion about the conservative vector field and the potential of a vector field, and somewhat mathematically, I know it's not accurate, you can consider the potential somewhat as the antiderivative. See, gradient roughly it is for the derivative, right? So accordingly, the scalar valued function, it is the antiderivative of the vector field, right? Roughly, okay, roughly. And also, if you wonder how we consider vector field as a conservative or not, the conservative concept really comes from physics. It is about energy conservation. So accordingly, the gravity, it is a conservative vector field. And then still mostly we focus on the mathematical part, mathematical discussion. And then given a vector field, how do we know if a vector field it is conservative or not? So we do have a criteria. It's a cross-parcel derivative property. Okay, basically it's either for a two-dimensional vector field, if dp dy turns out to be exactly the same as dq dx, then we say this f, it is conservative. For example, I'm having very simple vector field y and negative x. It is not conservative because dp dy, as you can tell, that's 1. And the dq dx, it's a negative 1, right? So dp dy, dq dx, they are not the same. So it is not conservative. And also, if I make a small change, I make the vector field as y and x. And then it turns out to be conservative because dp dy, dq dx, they are the same, just 1. So it is conservative. Okay. And also, another thing about the cross-parcel derivative, certainly we do have the quite similar criteria for for three-dimensional vector fields. But anyway, for now, we are just considering two-dimensional vector fields. We say it's a cross-parcel derivative because p, it is supposed to be along the x direction, the x component. Q, it is for the y component. But when we take the partial derivative, we consider dp dy and dq dx. See? Kind of cross things, right? dp dx, supposedly we should have. But anyway, we do dp dy and then do dq dx. That's the cross-partial derivative property. If the cross-partial derivative property holds, then f, it is conservative. I think this should be it for section 3. Actually, this is really chapter 6, 6.1, vector fields. Thank you for watching.